In this problem, we are going to look at static equilibrium on a beam. In particular, we're going to focus on the static equilibrium of the external loads on this beam. We can draw a reaction moment and force, so this is the force Fr, this is reaction moment Mr, from the wall on the beam as such. We do not need to follow a convention when we draw this reaction moment and force, but it's often a good idea to use our intuition to have an idea of what direction should we make these to produce positive magnitude or positive values for these particular loads. Now, there is a force P acting on this end over a very long span of 58 meters. We're suspending reality and essentially ignoring the mass or the weight of this beam. Maybe we're in a microgravity environment and we're applying this very small load of 1 newtons at the end. Nonetheless, what we want to do here is create an algebraic equation that describes the balance between the mr and the p and takes into account the length as well. So when we write that the summation of the moments is going to be equal to 0 for this balance of these parameters, as we just suggested, we do need to select a location at which we are performing our equilibrium of moments. And I've selected the right side. You could have selected the left side. That's fine. When we select this location, we should also designate which direction is going to be a positive torque or positive moment. And by putting a dot and not an X here, we are saying that positive is coming out of the board, so in the positive Z direction. So now we're going to consider the loads that contribute to moments about this point on the right side. P is acting through the point, so we don't have to consider P, but Fr has a lever arm of L, and so we see that we have FRL. Is it positive, negative? Well, we've drawn it as negative. Why is that? Because this force is going to be inducing a torque that's going to go into the board. Mr, on the other hand, is counterclockwise, and that's coming out at us, which means that we're going to be seeing a positive contribution. Mr is going to be equal to FRL. Now, what is FR? FR, we skipped external equilibrium on the forces, but we see there are only two forces here. And if we said that Fr were positive and P were minus, or vice versa, we would see that Fr and P balance each other, which means that Fr becomes P, this becomes PL. Now, we can perform some substitutions. We can put in a P of 1 Newton and an L of 58 meters, and we get 58 Newton meters. The question, though, is asking us to provide our response in units of foot-pounds. So we need to go ahead and provide a little bit of dimensional analysis and a conversion between foot-pounds and Newton meters, as we see here, and the result is that we have 42.8 foot-pounds. Now, problem is solved, but I would like to show a couple of approaches to doing this numerically. Again, this is pretty simple numerically at this point, but I think what you'll see here is powerful as we proceed in the class. So in using Google, we can just say 1 Newton times 58 meters initially, and this will give us a response in joules. Well, joules are units Newton meters. I didn't know we were doing a statics problem where we kind of care more about torque than we care about energy, but it went ahead and it calculated things in its units. This, though, indicates that a simple Google search is capable of handling units, which, as you've seen with our efforts in Python, we have to keep track of the units ourselves. So we can do 1 Newton times 58 meters in foot-pounds, and it will give us a result of 42.8 foot-pounds. So if you have multiple units, and we will during the class, it's often simple to use Google to keep track of your units. Now, let's go ahead and now you can stop the video if you want, but I'll go ahead and provide a complete follow-up to that by doing the work by hand in Python using Google Colab. So we go ahead and we once again import NumPy as MP. We can run this by either hitting Control Enter, we create a new cell, and again, you don't have to do each problem in a whole new notebook or script, but anyway, we're doing that here. And what do we say? We said that P was equal to 1 Newton, and we said that our length was equal to 58 meters. And of course, Python is not keeping track of these units for us. MR was going to be equal to P times L. And I guess we'll go ahead and, well, I'll show you a couple of different ways. Well, this will be then in units of Newton meters, and we can do a print MR equals MR, and we'll do 1 decimal point, and we'll say that the units are Newton meters. That's fine. That's a result valid, and it doesn't have the conversion to foot-pounds. But I can do it a variety of ways. Like I was tempted to add that conversion ratio in the original equation, but I can also do it in here. So it's 0.738 foot-pounds in a Newton meter. And so I've multiplied by 0.738 there, and then I'll just put foot-pounds here like that. So in this case, now you can see a result that has given us the MR in Newton meters and also in foot-pounds. All right, thank you for your time.